So, what is quantum entanglement? Quantum entanglement occurs when two particles or events are created from one at the exact same time and place, meaning that they cannot be described or observed individually. In other words, consider entanglement between particles to be like sharing an existence. For example, if the spin of one entangled particle is known, then the spin of the other can also be predicted with perfect accuracy, as seen in this expression. Particles can be entangled in different ways. The most common experimental method is to emit energized photons through certain crystals to convert them into entangled photons. When particles become entangled, any action or measurement done to one will instantaneously be performed to the other. When this happens, however, entanglement is immediately broken. This instant transmission of information can occur at any distance. While this sounds crazy, it is also very spooky. Information being transmitted instantly would have to be faster than the speed of light, which goes against Einstein's theory of relativity. In fact, Einstein himself once referred to entanglement as spooky action at a distance. The measurements for entangled pairs are like this because they share a quantum state. Quantum states describe the probability of each observable occurring for each possible measurement. And now, to better elaborate on these concepts, my colleague Mark will go through and expertly explain how we can relate quantum states to experimental applications.
Gee, thanks, Anthony. Here is a practical example of what we just said by having a photon with a packet of energy splitting in two and flipping the particles in cesium blocks. But that's complicated stuff, so let's make this easier. Here we have my nephew's cat, Patches. And we put him into an indestructible box with a bomb that has a 50% chance of going off at some point after the lid is closed and a minute afterwards. Now, if we don't open the box, we can't really say if Patches is alive or he is dead. If we used a wave function to describe Patches' state of being, we'll have a combination of the wave function of Patches being alive and a wave function of Patches being dead. And thus, Patches is technically in a quantum state of being alive and also dead at the same time while still inside of the box. So, let's see if Patches is still here. God damn it, Miguel, take over. I have to clean this up.
Thanks, Mark. So as Mark is cleaning his nephew's cat's mess, I will start talking about some applications. One application is quantum computing, and quantum computing is actually not so difficult to understand, and we know some of the basic ideas. The first idea is superposition. Because particles can be in either state, we can write a linear combination wave function of all possible states. This function will then be applied to the quantum computer, and it would allow for it to operate. The next idea is binary systems. All classical computers operate using a binary system of zeros and ones, which are called bits. However, quantum computers read zeros and ones simultaneously and are called qubits. Now, you might be wondering, simultaneously, this sounds very familiar, and if you are thinking about commutators, then you are right. Because quantum computers read zeros and ones simultaneously, as well as affect each other, we can consider them non-commuters and commuters. As you can see, quantum computers and quantum entanglement share similar ideas. So now I will hand it off to Anderson, who will talk more about the applications of quantum computing.
So quantum cryptography, where do I start? It is basically all of the nuts and bolts that keep your personal information private. If quantum computers came along and implemented quantum cryptography, well, everything you have, all your personal information, digital, it's open for anyone who has this quantum computer because it can break any code down in seconds. Also, it can create its own unbreakable code because it has qubits to consider both zeros and ones at the same time. That said, quantum cryptography has also led to some astounding models in science, considering that it can lead to alternate possibilities people haven't even thought of yet. Quantum entanglement as a whole has also led to the idea of teleportation. Because of a shared quantum state, Many things can have one thing transferred to it, while the other end also receives it. In case in point, 2017, the Chinese launched an experiment where they transferred energy to two connected objects, one in a lab and another in a satellite hundreds of miles away. And guess what they found out? You transfer energy to one, it's divided in half, and that half is sent to the outer space satellite. I know it blows your mind, right? And to top it all off, it didn't cross the space. It was just up from here to there. Information can also be teleported in the same way. No signals, no wires. So if we can do that with information and with energy, why can't we do it with humans? So you're probably wondering why this stuff isn't even heard of in your average daily lives. Very simple. Why? When it comes down to it, it is pretty darn expensive. Simply put, the energy bill that you would have for a personal computer that runs on quantum, well, let's say there are building energy bills that have cost less. In addition, all those liquid helium and nitrogen tanks you would need to keep this intact, that ain't cheap either. Not to mention that you have to keep it in sub-zero temperatures for quantum computers to function at all and keep their quantum state intact. To put it mildly, we've gone a great deal with quantum entanglement. We have made great bounds, but we also have a long way to go. So we call on you to come and join us. If any of you are interested, buckle up and get ready for a long ride. We could always see more bright minds like you advance this field. This presentation was made for viewers like you and our grade, mostly our grade. Thank you.